Hello everyone, this is going to be a quick crash course on electrolysis for O levels, iGCSE 06205070, Cambridge, Edexcel. So anything ninth and 10th classes. Now we're going to begin and we're going to talk about what really is electrolysis. So it is the decomposition, which basically means breakdown. So it's the decomposition of an electrolyte by passing current. So you pass current through something and it breaks down. What is that something? That something is called an electrolyte. It's a solution or a liquid that contains free moving ions. So it's got a lot of ions that are freely moving around. So they're basically ionic compounds like NaCl, it's got Na plus 1, Cl minus 1. Acids, for example, HCl, that's got H plus 1 and Cl minus 1. Or you're going to have your bases, hydroxides, oxides. But electrolysis would only be possible if you have free moving ions. So free moving ions can only exist in liquid or molten state, or you can have aqueous state. So for example, here in front of you is your ionic lattice. For example, there's a metal positive ion, Na plus 1, and you've got Cl minus 1. So they're all strongly attracted to each other. Uh, and remember, I'm pointing it to NaCl. So there will be billions of sodium ion Cl ions crystals forming a crystal, all attracted to each other very strongly. And since the force of attraction is very strong, the ions cannot move in the ionic lattice, which means that you're not going to have free moving ions. So no electrolysis is possible in this case. So no electrolysis is possible. But what if we melt it, or now when we melt it, the ions over here will be free to move around, and that is when electrolysis would be possible. Or when you have aqueous state. So this diagram clearly shows that the crystal over here, in molten state at very high temperatures, the ions would be energetic and they'd be able to move around. So the positive and negative ions are all slipping and sliding because they are in molten or liquid state. Or when you mix them in water, and when you mix them in water, the ions dissociate. For example, they get scattered in water, so there are water molecules everywhere, and the ions are floating around in water, so they're able to move around. Okay? This is what happens when you take a table salt crystal and you mix it in water and you stir it with a spoon. The ions dissociate, they separate, they go their separate ways, and they get scattered in water and they're able to move around. So in both cases, aqueous state and molten state electrolysis would be possible. They'll have free moving ions. In solid state, electrolysis is not possible because the ions or the charged particles, they can't move. Now let's begin the first type of electrolysis, which is the electrolysis of molten electrolytes. So this is obviously happening at very high temperatures. You're taking ionic compounds and you're heating them and you're melting them so that the ions are able to move around. Now this is your typical electrolysis diagram. There are many versions of this, but this is normally your typical diagram, and there's this battery in the middle over here. Now this side, the one where the bigger side is the positive side, and the other side is your negative terminal. So every battery, you can take your remote cell and have a look. It's going to have a positive side and it's going to have a negative side as well. So for example, you can just open a car battery and you can see there's a plus terminal, there's a minus terminal. You can open your remote cells, plus terminals and minus terminals are all written in front of you. Now coming back to our diagram, you got this negative side and there's an electrode that's attached to it. These are your terminals. Electrodes are attached to the positive side and they're attached to the negative side. And the negative side electrode is known as a cathode, and the positive side electrode is known as the anode. And in this case, we're dealing with graphite electrodes. The terminals are made out of graphite. Graphite is a very good conductor of electricity. It's got free moving electrons. So electrons could flow in the wire and this electrode very, very easily. So they've got free moving sea of electrons, and those electrons will help us conduct electricity. Now, what your battery would be doing is that at the cathode, it will be sending electrons. That's what the negative terminal does. It provides electrons. So electrons are flowing towards the cathode and they're accumulating on this electrode over here. So you're going to see a lot of electrons on the cathode, which is why the cathode will have a negative charge, and there'll be a lot of electrons coming towards that side. So the battery is constantly providing electrons which are accumulating on the cathode. And on the positive side, the battery is taking away electrons. So when you take away electrons, positive charge builds up, because whenever something loses electrons, it's going to have a lot of positive charge. So on the anode, there's going to be a lot of positive charge that will be building up. And that's what's going to happen. That's the movement of electrons. Negative side electrons are traveling towards the cathode. Positive side electrons are being pulled back into the battery. Now, what you're going to do is you're going to dip those electrodes, cathodes and anodes, into a solution. Not a solution, but right now we're dealing with molten. Solution refers to something dissolved in water. So right now we're dealing with molten electrolytes. So let's talk about a molten electrolyte that's got free moving ions like NaCl, any ionic compound, NaCl, and it's molten, so that's in liquid state. So there's going to be a lot of sodium ions and Cl ions that would be floating around. So your electrolyte at the moment at high temperatures NaCl is molten, so lots of sodium ions and Cl ions all freely moving around in this electrolyte, molten electrolyte. But when you connect or put these cathodes and anodes into the molten electrolyte, what is now going to happen is that the cathode is negatively charged. When you have a negatively charged cathode, what's going to happen is that negative sides, negative charges, they attract positive ions. So all my positive ions, which are known as cations, the reason they're called cation is that they get attracted to cathode. So all my positive sodium ions are going to get attracted to the negative cathode where there's a lot of electrons which are already negatively charged. So negative charges, they attract positive ions. So all my positive ions are going to get attracted to cathode. Similarly, the anode, which was my positive side, is going to attract all the negative ions. So all my Cl ions in the electrolyte are going to get attracted to the positive anode. Now here's the current situation. Positive ions attracted to cathode and all the negative ions sticking to the anode. What's going to happen next is that these positive ions over here are going to gain electrons. Battery is sending electrons and they're going to start to gain electrons. So the battery is pushing electrons and those electrons would eventually reach the sodium ions over here. So we're going to learn how to write the half reaction that's happening at the cathode. So sodium is +1, which means that it's short of 1 electron. +1 means that it lost 1 electron somewhere. So that's why it's got a positive charge. So +1 means that it exactly needs 1 electron. So I've got this sodium +1, and the battery is pushing electrons onto the sodium ion. So it's going to gain exactly 1 electron. And that will turn sodium ions into sodium neutral atoms, which will exist because they are metals. They're going to exist in metallic form, and you're going to see shiny sodium metallic metal depositing over here. So you'll start seeing metallic sodium. Now focus closely on the other side. You had all these negative ions attracted to the positive anode, and the battery is pulling electrons out of them. So Cl-1 means that it's got 1 extra electron, which is why it had a -1 charge. So the battery is going to pull that electron out of it. So your reaction. So I'm going to write Cl-1, and what's going to happen is that the battery is going to take away 1 electron out of it. So 1 electron produced, and that's given to the battery. Cl-1 loses 1 electron. That's taken up by the battery, and it's going to become neutral because now it doesn't have any excess electrons. So that's my half equation or half reaction at the anode. Now at anode, you also have to be careful about something. You have to be careful about cathode as well, and that something is that there are certain elements which, when they become neutral atoms, they never exist as single atoms. They're always diatomic molecules, and that includes your entire group 7. So chlorine atoms don't exist. Chlorine is always in the form of Cl2. Two chlorine atoms, they combine and they form a Cl2 molecule. Same with bromine, same with iodine. Iodine neutral atoms don't exist. Two iodine atoms would combine and they're going to form a molecule of I2. Hydrogen as well, oxygen, nitrogen, they're all diatomic. So the trouble with our equation at the moment is that a Cl atom alone is not going to exist. So there's always going to be two Cl atoms combined together and they'll be forming a Cl2 molecule. So what I'm going to do over here is I'm going to double everything because I need two Cl atoms. Cl as a single atom is never going to exist. So what I'm going to do is I'm going to double everything. So what will happen is I'll have two Cl ions, and those two Cl ions would form two Cl atoms and they'll join together to form a Cl2 molecules. And since I've doubled everything, 2 electrons are going to be produced. So remember, this is exactly the same equation, but I've doubled everything because a single Cl atom is not going to exist. It's going to exist as a diatomic molecule. So Cl ions were losing 1 electron, Cl ions were producing 1 electron, and they were becoming Cl atoms. But since it's diatomic, I would need 2 Cl atoms, so I doubled everything, 2 Cl ions. They're going to produce 2 Cl atoms, which would join together to form Cl2. And as a result, they're going to produce 2 electrons. So that's my equation at anode. And the other thing you got to remember is that Chlorine, you have to remember, there's going to be a lot of questions on observations. Now, observations are not, whenever they ask you about observations, they're not asking for an equation, they're asking what you're going to see. So what you're going to see over here is that you should know that chlorine gas, when it gets produced, that's a greenish yellow gas. And since it's a gas, you might notice bubbles being produced in the liquid. So you'll start noticing bubbles being produced over here. Now, I'm just going to add one tiny bit over here. That is that at cathode, it's always a gain of electrons, and the term that's used to represent gain of electrons is a reduction. So keep this in mind that Na plus 1 is getting reduced. It's undergoing reduction. It's gaining electrons. And vice versa, at anode, the substance over there is always going to lose electrons, and the term that's used for losing electrons is known as oxidation. So Cl minus 1 over here is getting oxidized. It's losing 2 electrons, so that is oxidation. So reduction always happening at cathode, oxidation always happening at your anode. Another thing that I wanted to add was that we're using graphite electrodes. Now remember, your graphite electrodes are referred to as your inert electrodes. There's another electrode that's also inert, and that's known as platinum electrodes. Now, both of these graphite and platinum electrodes are really good conductors of electricity, and they're inert. They are very, very unreactive, which is why they're always very good to be used as electrodes, because you don't want them to react. You just want them to conduct electricity. One sending electrons, the other one anode that's gaining electrons, and sending those electrons back to the battery. Now, let's move to the next question, which is going to be exactly the same. Now, here you can see that I've drawn the diagram back again of the same cathode anode. I'm going to do the electrolysis of another molten electrolyte, and let's say this time it's MgO in molten state. It's in liquid state. Magnesium oxide has Mg, which is group 2 plus 2 ions, and O minus 2 ions. So all my magnesium ions are getting attracted to the cathode, which are positively charged ions, and all my oxide ions, O minus 2 ions, are getting attracted to anode. What's going to happen at cathode? The battery is going to send in electrons, and Mg plus 2 over here is going to gain electrons. So my half equation at cathode would be Mg plus 2, and the battery would send in electrons. So Mg plus 2 is in need of 2 electrons. So it's going to gain 2 electrons, and it's going to become magnesium back again. While O minus 2 on the other side, the battery is going to take away electrons. So your O minus 2, so let me have my O minus 2 over here on the other side. It's going to be losing 2 electrons. It's got minus 2, that means it's got 2 extra electrons, and the battery is going to take away those 2 electrons. So it's going to be losing those 2 electrons. So here's the 2 electrons lost, and a neutral oxygen atom is going to be produced. And that's my anode equation. That's my oxidation equation, where the oxide ions are losing electrons. Now, again, we're going to come back to the point, which is that oxygen is diatomic. You don't have single atoms of oxygen. Oxygen atoms, they always combine with other oxygen atoms to give you an O2 gas molecule. So I'm going to double everything. So it's going to be 2 O minus 2 ions, and it's going to produce 2 oxygen atoms, which will combine and they'll form an O2 gas molecule. And since you got 2 oxide ions, they'll be losing 4 electrons because I've doubled everything. So that over here is my equation at anode. So make sure, be careful about elements that are diatomic. So oxygen atoms don't exist as single atoms. They always exist as O2 gas molecules, which is why I doubled everything. And I wrote O2 gas molecule. And again, they're going to ask you for observations. So when oxygen gas is being produced, you're going to notice bubbles of oxygen gas. Colorless bubbles. Oxygen is a colorless gas. 21% of the atmosphere is oxygen gas. And on the other side, you're going to see metallic Mg getting deposited. Now, here's the next electrolysis of, and this time it's molten aluminum oxide. So at high temperatures, aluminum oxide has a melting point of around 2000 degrees centigrade. So a really high melting point. So you're going to melt it. Aluminum oxide is molten. So you've got this liquid, and you've dipped your cathodes and your anodes into it. Now your cathodes and anodes, the negative side, battery is sending electrons, and the positive side, the battery is taking away electrons. Aluminium oxide has 2 ions. One of them is Al plus 3. Al is in group 3, and the other one is oxygen, and that is minus 2 ions. Oxygen is in group 6, aluminium is in group 3. So these are the respective charges. So your liquid has all these ions and it's a liquid state, so the ions are moving around. Now the negative cathode will attract all the positive ions. So all Al plus 3 ions are going to go and they're going to stick to the negative cathode. And your positive anode over here is going to attract all the negative ions. So all the O minus 2 are going to go and stick to this. So you can see all the O minus 2 ions getting attracted to the positive anode. So what's going to happen at cathode? At cathode, the battery is going to send electrons, and your Al plus 3 ions over here are going to gain electrons. So what's your equation? Your equation is going to be that your Al plus 3 would be gaining 3 electrons. They need 3 electrons, and they would become aluminium. Neutral aluminium metal is going to be formed. So there's going to be a coating, a silverish coating of aluminium. Molten aluminium is going to be produced at the cathode. So you can see a silverish metal deposited. So shiny metal deposit. And on the other side over here, O minus 2 ions, the battery is going to take away electrons from it. So you're going to have your O minus 2. So your O minus 2 would be losing electrons. Minus 2 means it's got 2 extra electrons. And your O minus 2 is going to give those electrons to the battery. So O minus 2 would lose 2 electrons, so 2 electrons are lost. And it's going to become a neutral oxygen atom. But again, remember I told you that some elements were diatomic. I gave you a list. So oxygen is one such atom. It's not going to exist as a single atom. It's always going to exist as a diatomic molecule. So I need to double everything. So there's going to be 2 O minus 2 ions. And they're going to lose 4 electrons because I've doubled it. And 2 oxygen atoms are going to be produced, which will join together to form an O2 gas molecule. So O2 gas molecule, and what you're going to notice is bubbles of O2 gas. Bubbles of O2 gas will be produced. And remember, these are graphite inert electrode. So specifically for graphite or platinum. You don't use platinum because platinum is pretty expensive. Normally it's graphite electrodes. Like in the laboratory, if you do this, you're going to use graphite electrodes, which are inert, unreactive. Their only purpose is electric conduction. They're not going to do anything themselves. Now your decomposition is complete. So this is what electrolysis is. Aluminium oxide was one compound, but now it's separated. Aluminium has been produced on one side, oxygen gas has been produced on the other side. Now let's do another electrolysis very quickly of molten lead chloride. Again, something that's got a very high melting point. So again, I'm going to try and do this very quickly. So my liquid, I've dipped my cathode and anode. So you can see my cathode, you can see my anode. Lead chloride has 2 ions. One of them is lead plus 2. Remember, Pb has 2 charges. It's plus 2 or plus 4. They're going to tell you, TK, you don't have to worry about it. They're going to tell you that this is lead 2 chloride. That's the formula. And the other one is Cl, that's group 7, so it's got -1. So remember, you should know how to figure out the charges on the elements that are in the compound over here. So lead plus 2, Cl -1. Now, all the positive ions in the liquid are moving around. It's in liquid state. So the lead plus 2 ions are going to get attracted to the negative cathode. So you'll have a lot of Pb plus 2 ions over here. And all the negative ions, Cl -1, are going to get attracted to the positive anode. And they're going to accumulate or stick to the positive anode. So you can see the lead ions on the cathode. The battery is sending electrons. So the lead plus 2 is going to gain electrons. It's going to get reduced. Reduction is the word when something gains electrons. So my equation over here will be that my Pb plus 2 is going to gain how many electrons? Plus 2 means it needs 2 electrons. So it's going to gain these 2 electrons and it will become Pb. So lead metal is going to be formed. Again, a metallic shiny deposit is going to be observed over here. On the other side, you've got your Cl ions and they're going to lose electrons. The battery is going to take away electrons. So make sure you learn how to write this equation correctly. So you got these Cl ions and these Cl ions are going to lose 1 electron because your Cl ion has 1 extra electron. So it's going to become a neutral Cl atom. And again, Cl, remember, is diatomic. It's group 7. So group 7 is entirely diatomic. So a single Cl atom is not going to exist. So I'm going to double everything. So I'm going to have 2 Cl ions, and together they're going to lose 2 electrons, and 2 Cl atoms are going to be produced, which will join up and they would form a Cl2 gas molecule. And that's going to be my equation at my anode. And Cl2 gas, what is going to be the observation in this case? Cl2 gas. Now Cl2 gas is a greenish yellow gas. So you will notice bubbles of a greenish yellow gas forming at your anode. And that's it. That's your electrolysis of molten lead chloride. The next thing that we're going to try and do is we're going to try and do electrolysis of aqueous solutions using inert electrodes, which is again graphite or platinum. Graphite is the cheaper option. Platinum is the more expensive option. So inert electrodes, so the electrodes are not doing anything. They're only conducting electricity. They're sending electrons from one side, pulling electrons from the other side. That's what the battery is doing. So the electrodes are just conducting or moving, helping the electrons move along. Now we're going to come back to aqueous solution. So what's different from molten? Aqueous means that there's going to be the salt or whatever the compound is. It's going to be mixed in water. So the electrodes would be dipped in water. There's H2O molecules. And the thing with water molecules is that they tend to break down and they tend to produce H plus 1 and OH minus 1 ions, hydroxide ions and an H plus 1 ion. So you'll have lots of water molecules. So you can see over here, some of them would, I'm breaking this one. So the water molecule, the bond between the O and the H might get broken during collisions. The OH will get a -1 charge, and the H over here will get a +1 charge. So two ions are going to be produced. Some other water molecule somewhere else, maybe this one would get broken down, its bond might get broken. So I'm going to rub off the bond, and it's broken, and get rid of that. And the OH might get a -1 charge, the H would get a +1 charge. And let's break this bond as well. So OH and H plus 1 and OH minus 1. Now the reason why you're getting H plus 1 is because the H always leaves electrons. It's not very strongly attracted to its electrons. So it gives the electron to the O, which is why that one gets a negative charge. This one gets a +1 charge because it lost an electron. Anyways, so the point of the whole thing is that whenever you have water in the solution will have two ions, H plus 1 and OH minus 1 ions. So there's going to be two extra ions. Now in the previous cases that we have seen, for example, if you look at the molten electrolysis that we did earlier, there was no H plus 1 or OH ions anywhere in the liquid because there was no water in it. You can remember when aqueous is written, there's going to be water in the solution. So that's it. So remember, aqueous means water and H plus 1 and OH ions would be part of the solution. So we're going to try and do the first electrolysis. So here's the electrolysis of copper sulfate aqueous. And we're going to try and do that using inert electrodes. Remember, let's focus on this inert electrodes, okay? Graphite or platinum. So copper sulfate. So what ions would be present in our solution? And it's aqueous. Aqueous would be written as AQ. So my solution would have copper, which is in this case +2. And it's going to have SO4, which has a charge, sulfate ions, which have a charge of -2. Plus, since it's aqueous, there's going to be two more ions. There's going to be H plus 1 that's going to be present in the solution. And there's going to be OH minus 1 ions also part of the solution. So now in the previous case, we had liquid. Now you've got 4 ions instead of 2 ions. You've got extra ions coming from the water itself. This is your cathode. That's your anode. And the battery is sending electrons from the cathode and taking away electrons from the anode. Your solution now has 4 ions. The negative cathode will attract the positive ions over here. So it's going to attract copper +2. And there's going to be ions coming from the water as well. So there's going to be lots of copper +2 ions, lots of H plus 1 ions over here that will be sticking to the negative cathode. Vice versa, your positive anode over here will attract all the negative ions that are part of the solution. So the negative ions in our case are going to be OH minus 1 and SO4 -2. So lots of OH minus 1 and SO4 -2 ions that would be negative ions attracted to the positive anode. Now you can clearly see that the electrons are coming in at the cathode and they're going to go to these ions. So those electrons can be gained by, so who's going to gain those electrons? Those electrons can be gained by copper +2, or they can also be gained by H plus 1. So the battery is sending electrons and someone over here is going to gain those electrons. You got a bunch of ions over here and they're going to gain electrons. But now we've got a different issue. The issue is that you've got two options. It's either copper +2. So who's going to get reduced? Who's going to gain electrons? Is it going to be copper +2 or is it going to be H plus 1? That's the question mark. So one of the ions has a greater tendency, a much higher tendency to actually gain electrons compared to the other one. Remember, you've got different ions. Different ions have different attraction for electrons. copper plus 2, H plus 1, both of them don't attract electrons equally. So one of them has a greater tendency to actually get reduced to attract electrons, to gain electrons. How do we figure that out? The way you're going to figure this out is that there's going to be a series that you have to remember. Now I've written the series down over here. So there's a series of, this is known as the reactivity series as well. So it's a list of ions of different elements. So you got potassium, sodium, calcium, magnesium, aluminium. Carbon is just there for a reference. We're going to talk about that later on. Zinc, iron, tin, SN is tin, lead, that's lead metal, hydrogen, again, that's that's going to be part of the series as well. There's copper, mercury, Hg is mercury, Ag is silver, Au is gold, and Pt is platinum. Now the ease of discharge increases down the group. Down this series. So that basically means that as you go, the one that's at the bottom of the series is the one that likes to gain electrons. So again, I repeat, the ones at the bottom are the ones that really like to gain electrons. So we're going to come back to our question. So you have to remember this entire series by heart when you're dealing with aqueous solutions. Why? Because now there's a competition going on for electrons. The electrons are coming in, and you've got two options, copper plus 2 or H plus 1. Who's the one that really likes to gain electrons? Is it going to be copper plus 2? Is it going to be H plus 1? So we're going to look at the series and we're going to see who wants to gain electrons, copper plus 2 or H plus 1. So you can see over here that H is over here, and you can see copper being over here. So the competition is between copper and H. Who likes to gain electrons? Remember, the one that's at the bottom of the series, the one that's less reactive, is the one that really likes to gain electrons because it doesn't like to lose electrons. It's not very reactive. So it's going to try, if it's an ion, it will try to be, it's going to try and gain its electrons back. So we're going to select copper. So we go back, and we've now realized that between copper and H, it's copper that's the one that really likes to gain electrons. So the electrons, I'm going to rub this off. The electrons will not be going to H. So H plus 1 ions, nothing would be happening to them. The electrons are coming in and they're getting attracted by copper plus 2. So we've figured out that in our case, it's going to be copper plus 2, and I can write an equation for that. So it's going to be copper plus 2. And that copper plus 2 would gain how many electrons? It needs 2 electrons. So it's going to gain 2 electrons from the battery. And it's going to form copper metal. So you would start seeing copper metallic deposit forming on the cathode. So a shiny pink metallic deposit of copper would form over here. So again, I'm just going to quickly recap. Aqueous solution, you got more ions, more than one ions at the cathode. And between those ions, you're going to try and figure out who's going to gain electrons. So you're going to look at in our case, we had copper and H. So we're going to look at the reactivity series, which is this one, the ease of discharge. And you had copper and H. The one who's at the bottom of this is the one whose ion really likes to gain electrons. So it's going to be copper in our case. And let me just briefly tell you that it's always the unreactive metal that wants to gain electrons because it doesn't like to lose electrons. So if it has lost electrons, it will try to gain its electrons back. It does not want to react. Copper would try to remain in the form of copper. So if there are copper plus 2 ions, they will quickly try to gain the electrons back. But all you have to remember is, just keep things simple. All you have to remember is that between copper and H, you're going to go for copper, the one that's at the bottom. And so the electrons at cathode would be going to copper, and you can write the equation, and that's it. Okay, so that's your equation at cathode. Now what we're going to do is we're going to talk about the other side, which is the anode side. And we're going to try and figure out who's going to lose electrons to the battery. The battery is trying to pull electrons away from it, from OH minus 1 or SO4 minus 2. You've got two negative anions at your anode. So is it OH minus 1 or is it SO4 minus 2? Now for this, you've got another series because one of the two has a greater tendency to actually lose electrons. And I'm going to write down that series. Now here's my series at the anode, whether it's going to be OH minus 1 or it's going to be SO4 minus 2, who's going to lose electrons. So we've got another series. So the rest of the ions, whatever ions you've got, you can put them at the top. You don't have to remember the whole series. Just remember the last few parts. Cl minus 1, OH minus 1, Br minus 1. So the lower you're down, the lower you are in this series, the more likely you're going to lose electrons. So I minus 1 has got the greatest tendency to actually lose electrons, then Br minus 1, OH minus 1, and you've got Cl minus 1. Now in our case, we've got, at anode, you've got two ions, OH minus 1 and SO4 minus 2. So I have OH minus 1 and SO4 minus 2. I'm just going to put it over here. Okay, so OH minus 1 is lower in the series. So OH minus 1 is the one that's going to lose electrons. So I've selected my ion who's going to lose electrons, and that is definitely OH minus 1. More likely to lose electrons. So SO4 minus 2 will not do anything. OH minus 1 is the one that's going to end up losing electrons. Now for OH minus 1, you got to remember the equation as well. So that equation is this one. It's 4 OH minus 1s. They're going to lose electrons and they would decompose. When they lose electrons, they're going to form water and they will form an oxygen gas molecule, and they would produce or lose 4 electrons. So OH minus 1s, 4 of them would lose electrons. They will form water and O2, and they'll produce 4 electrons, which would be given to the battery. They're going to be taken up by the battery. So I'm going to again point this out. You got to remember this equation. You got to remember the equation for OH minus 1 losing electrons. So most other equations you can make them up, but for OH minus 1 losing electrons, got to write this. It loses 4 OH, negative ions lose 4 electrons, and they would form this thing. So make sure you remember this particular equation for OH minus 1. Another thing that I would like to add over here is that there is one tiny exception for Cl minus 1 ions. So that exception is that when you're talking about ease of discharge, who's going to lose electrons, if you've got a solution, that's an exception. Remember that. So let me restate what the exception is. That if there's a concentrated solution of Cl ions, a solution that contains Cl ions, and they have specifically stated that the solution is concentrated, then it's always Cl minus 1, which is oxidized or discharged or loses electrons. So forget this ease of discharge series. Remember, for Cl minus 1, you got an exception. If you got Cl ions and the solution is concentrated, then always select Cl minus 1, because that's the one that's going to lose electrons at the anode. So we're going to do another example just after this. But before moving to the next example, I'm going to write down the observations. The observation at your cathode will be that there's going to be a copper deposit, metallic deposit, that's going to be formed. Remember, you're already aware of what copper is. Copper is a metal, a shiny metal, and it's a pink shiny metal. So pink metallic deposit can be seen over here. And on the other side, your anode side, oxygen gas is being produced. And whenever oxygen gas or any colorless gas is produced, you're going to notice lots of bubbles. So you can see bubbles forming at this side, and bubbles are effervescence. Effervescence is the term that's given when bubbles get formed. So oxygen gas, whenever it's produced, bubbles would be seen. The next thing they're also going to talk about are about the changes in the solution. So remember, we had the electrolysis of copper sulfate aqueous, which had all these 4 ions. But at cathode, the copper ions are gone because they get deposited at the cathode. So what will happen is that the solution, all the copper ions will get used up, because all of them are going to gain electrons. They're going to turn into copper, and they're going to get deposited at your cathode, where the copper metallic deposit is going to build up. So the copper ions would be gone, and at your anode, it's the OH ions that are losing electrons to the battery, and they're turning into water and oxygen. So all the OH ions are leaving or going. They're turning into something else. They're turning into water molecules and oxygen gas, which will turn into bubbles, and it will also escape. So what's left in your solution? Your solution has H plus 1 ions, and it's called SO4 minus 2 ions. So this is what's happening to your solution, that your solution, which previously had all these ions, now the copper ions are gone, and the OH ions are also gone. So you're basically left with sulfuric acid, which is H2, H2SO4. How did I come up with sulfuric acid? Because H plus 1 and SO4 minus 2 is left. If they combine, they'll end up forming sulfuric acid. So your solution is turning acidic. It's turning acidic. And another thing is that the color of copper sulfate initially was blue. It's a blue solution. Remember the colors of your compounds. But now it's turned into sulfuric acid, which is colorless. Plus, it's obviously acidic. So these are the changes that are happening in your solution. The copper sulfate turns into sulfuric acid. The blue solution turns into colorless. So the color fades, and it becomes acidic. Now, in the next question, we've got the electrolysis of NaCl, aqueous, and dilute NaCl, aqueous. Now, first thing, remember it's the same diagram. You've got your cathode, the negative cathode, and it's inert electrodes. Remember, graphite or platinum electrodes are being used. So they are inert electrodes. They've been dipped into the solution of NaCl aqueous. The negative cathode is giving electrons, and the positive anode is from the battery is pulling electrons back again. Now, NaCl aqueous means that you're going to have Na plus 1 and Cl minus 1 ions. Na is group 1, so that's why I know that it's plus 1. Cl is group 7, so I know that that's minus 1. And since it's aqueous, there's going to be H positive ions and there's going to be OH negative ions as well. So we've got these two ions as well. And what happens when I dip the cathode and the anode into the solution? The positive ions, they get attracted to the cathode, which is negatively charged. All of them are going to stick to the cathode, and my negative ions over here in the solution are going to get attracted to the positive anode, which is connected to the positive terminal of the battery. So the positive ions are going to attract the Cl ions and the OH ions, while the negative cathode is going to attract the Na plus 1 and H plus 1. So all these ions, lots of thousands of ions, are going to get attracted to the cathode, and thousands of anions or negative ions are going to get attracted to the anode. So the question now again is, the battery is sending electrons. Let's focus on cathode first. The battery is sending electrons. So who's going to gain those electrons? Whether it's going to be Na plus 1 or H plus 1. How do we figure out who gains electrons? So how do I know who likes to gain electrons? So electrons are coming in. Na plus 1 or H plus 1. So we're going to look at the ease of discharge series, which is the reactivity series. And this time, we've got a competition between Na and H over here. So remember, the electrons are coming in. So either Na or H, someone is going to gain electrons. And remember, what did I tell you? I told you that the one that's lower down in the reactivity, they're the ones that, the lower down in the reactivity series, they're the ones, the unreactive ones that like to gain electrons. So over here, it's going to be H. H ions are the ones that like to gain electrons a lot. Remember, N is very reactive. N does not like to gain electrons. It instead, it's a metal, it likes to lose electrons, doesn't like to gain those electrons back. So remember that reactive metals, they always like to lose electrons. They like to form ions. They don't want to do the opposite. While the unreactive ones want to gain their electrons back again. They don't want to give electrons to anyone. So they want their electrons back. So we're going to go with H. H is the one that gains electrons. So the electrons over here, these electrons are going to end up with H. And the equation in this case would be that it's going to be H, which is plus 1. So this H plus 1 would gain an electron, and it will form a neutral H atom. But again, the issue is that H is diatomic. It never exists as a single atom. So I need to double everything. It always exists as a diatomic molecule. So we need 2 H atoms. So I'm going to double this. 2H would gain 2 electrons, obviously. And 2 H atoms would be formed. And they would together form an H2 gas molecule. So that's my equation. So that's my equation at cathode. That's what's happening at cathode. Now, coming back to the other side. Who's the one who's going to lose electrons, whether it's going to be OH minus 1 or Cl minus 1. So again, I have to look at the discharge series at anode. So here's my discharge series at anode, which is the same one. So I've got a competition between OH minus 1 and Cl minus 1 ions. So here is OH minus 1, and above that you've got Cl minus 1 ions. Now, the ions that are at the bottom are the ones that are more likely to lose electrons. There's an exception, which is that if concentrated solution, remember this is not a concentrated solution. So this exception highlighted in red is not applicable in our case. So forget that, ignore that. So it's just a simple competition between OH minus 1 and Cl minus 1 ions. So who's going to lose electrons? Between OH minus 1 and Cl minus 1, over here it's going to be OH minus 1 ions because they are lower in the discharge series. So the electrons that are going to be lost will come from OH minus 1. That's the one that's going to be giving electrons to the battery. And the equation for the OH minus 1, again, it's the same equation which I told you just earlier that you have to remember this. It's going to be 4 OH minus 1 ions. And they're going to produce 2 water molecules. And they're going to produce an oxygen gas molecule. And they're going to lose 4 electrons. Okay, so that's my equation at the anode, and I told you specifically that you have to remember this equation specifically for OH ions. So OH ions end up losing electrons. your solution will no longer have H positive ions at the cathode, and they're not going to have OH ions because they're going to turn into something else. So the H plus one over here will gain electrons, they're going to get reduced, and the OH ions on the other side are the ones that are going to get oxidized and they're going to lose electrons. So the OH ions are gone and the H plus ones are also gone. So in your solution over here, H plus one and OH minus one ions are gone. So I'm going to start writing the observations. The observation at cathode would be hydrogen gas bubbles. So it's either bubbles or effervescence, which is again, it's also the same. That also means bubbles. So colorless bubbles of H2 gas, and I'm going to draw some bubbles. So there's going to be bubbling seen. Hydrogen gas is going to be produced. The test for hydrogen gas is that it burns with a pop sound. So if you're able to collect the hydrogen gas over here, you can light it up and it will burn or explode with a pop sound, a tiny pop sound. What's the observation at the anode? It's the same, oxygen gas is being produced. So you're going to notice bubbles around the anode. So there'll be tiny bubbles that would be produced at the anode. And it's the same observation, which is bubbles or effervescence. So exact same observation, bubbles, effervescence. And let's also talk about what's going to happen to the solution. Remember, I told you that the H plus one ions are gone and the OH ions are gone. Solution does not have H plus one or OH ions. So what's going to happen to your solution? Nothing will happen. You still have NaCl. I mean, you started off with Na plus one, Cl minus one ions. So it's basically water that's getting electrolyzed. So your solution becomes more concentrated because you're going to have less and less water. So the solution becomes concentrated. As you can see that water is lost. H plus one and OH ions are getting used up. Water is lost. So solution becomes more and more concentrated. Now, very quickly, what we're going to try and do is we're going to try and do the electrolysis of aqueous NaCl, but this time the solution is concentrated. It's the same inert electrodes that I'm using. So let's quickly label this. So here's my negative cathode and my positive anode. What is the list of ions that are going to be part of the solution? So I've got NaCl, Na plus 1, Cl minus 1, and since it's aqueous, it's going to have, even if they hadn't told us that it's aqueous, if they have written concentrated, that means it is an aqueous solution. So it's going to have H plus 1 and OH minus 1 ions as well. The positive ions, Na plus 1 and H plus 1, are going to go in and get attracted to the negative cathode. And the positive anode is going to attract our OH minus 1 and Cl minus 1 ions. So they're going to go and stick to the anode. And what's going to happen to cathode? Some amount of Na plus 1 and H plus 1 would end up gaining electrons. How do we figure that out? So at cathode, we've got the same discharge series. And so there's Na plus 1 that's trying to gain electrons, and there is H plus 1 that is also trying to gain electrons. N is over here and H is over here. So the one that's at the bottom is the one that's more likely to gain electrons. So it's going to be H plus 1. And let me write an equation for H plus 1 gaining electrons. That's going to be H plus 1 needs an electron, will become neutral. But the question is that H is diatomic. So there should be two H atoms. They would join together to form an H2 gas molecule. So I need to double everything. So 2H plus 1 would gain 2 electrons, and they're going to form 2 hydrogen atoms, which will join up to form an H2 gas molecule. So you're going to see bubbles or effervescence, bubbles forming over here. And the electrons would be gained by H plus 1. And these H plus ions are going to get used up. They're going to be used up. They're going to turn into H2 gas and they'll form bubbles, and those bubbles will escape. So that's what's happening at cathode. We've written down the equation as well. Now I'm going to move towards the anode. Someone out of these two would lose electrons. And let's try and figure out whether it's going to be OH minus 1 that's going to give electrons or Cl minus 1 that's going to give electrons to the battery. So here I've pasted the ease of discharge series for the anode. And I've got a competition that's going on between OH minus 1 and Cl minus 1 ions. So you can see OH minus 1 or Cl minus 1. But remember, this is a concentrated solution, and I wrote down an exception for that. If the solution is concentrated, then you always go for Cl minus 1. Cl minus 1 are the ones that are going to end up losing electrons to the battery. So it's going to be Cl ions that would be losing electrons. So Cl minus 1 over here, and always remember that if it's concentrated, as you can see over here, it's always Cl minus 1 that ends up losing electrons. So the equation for Cl-1 has one extra electron, so it's going to lose that one electron, and it's going to form a Cl neutral atom. And Cl group 7 is all diatomic, so it's always a Cl2 molecule, not a Cl atom. So I need to double this. So I'm going to have two Cl ions. They're going to lose two electrons. Two Cl atoms would be produced, and they will join up to form a Cl2 gas molecule, which is this. So Cl2 gas molecule is going to be produced. So again, we're going to notice a greenish yellow gas that's being formed. We'll see bubbles of that greenish yellow gas forming over here at the anode as well. And now finally, what's going to happen to the solution? So the summary is that the H+1 are the ones that gain electrons because they're lower down in the reactivity seas. And over here, it's Cl-1 that loses electrons, because in the case of concentrated, it's always Cl-1 that ends up losing electrons. So you can ignore all of this. It's always going to be Cl-1 if the solution is concentrated. Now what we need to do is what changes are happening to our solution. So our solution had all these ions initially, Na+1, Cl-1, H+1, and OH-1. The H+1 are gone, and on this side, Cl ions are also gone. They're going to get used up. So the H+1 are gone, and the Cl ions are gone at the other side. So what does your solution have at the end? What's left in the solution, that's Na+1 and OH-1. So my solution changes from NaCl concentrated, and it has now become alkaline. It's NaOH, Na+1 and OH ions that are left. So that's what's left, and that's a basic solution, or you can call it an alkaline solution. Now let's just do quickly another electrolysis of silver nitrate aqueous. Again, I'm using graphite or platinum electrodes, inert electrodes. Here's my cathode, the negative side, the smaller terminal, and the positive anode. Sending electrons, cathode sending electrons, positive anode taking away electrons. I need to figure out what are the ions that are present in silver nitrate aqueous. So there are obviously silver +1, NO3 -1 ions, and there are going to be two more ions. One of them is going to be my H+1 ion, and the other one is going to be my OH-1 ions. They are coming from water. So I've got these four ions. The negative cathode will attract all the positive ions. So Ag plus and H+1 are going to get attracted to the negative cathode, and the positive anode is going to attract all my negative ions. So the negative anions are getting attracted to anode. Now the next thing is I need to figure out who's the one who's going to gain electrons at cathode. The electrons are coming in. So is it going to be Ag+1 or is it going to be H+1? So I will open up my reactivity seas, the ease of discharge. So the competition is between Ag+1 and H+1. And we need to find out whether these electrons are going to be attracted by Ag+1 or whether H+1 likes to attract electrons. So I've got Ag+1 over here, and I've got H+1 which is over here. Now the one that's at the bottom of this series, that's the one that's more likely to gain electrons. So it's going to be silver ions that are going to have a greater tendency to actually attract electrons. So the electrons coming from the battery would end up, they're going to come and they're going to be gained by Ag+1 ions. So we can write an equation. So it's going to be Ag+1 that would gain electrons, and it is going to form Ag. And hence, what you're going to notice is a shiny silver deposit is going to be built up on the cathode. So over here, you would notice a shiny silver deposit that's going to form at your cathode on top of the electrode. So that's what's happening at your cathode, and your silver ions are going to get used up. So you'll only be left with H+1 in this solution, because all the silver ions would end up gaining electrons and they would turn into silver. So we figured out what's going on at cathode. Now we're going to move towards our anode. We need to figure out who loses electrons. Is it going to be OH-1 or is it going to be NO3-1? So again, I've brought up my ease of discharge series. So it's OH-1 or NO3-1, and you can see that OH-1 is over here. So let me mark that. So I've got OH-1, and the rest of the ions, the NO3-1 ion is going to be up here somewhere. So remember, you don't need to remember the whole series. Put any other ion over here. Rest of the ions, just put it over here. Again, it's the bottom one that's the one that's going to lose electrons. So the electrons that will be gained by the battery would be coming from, they're going to be lost by OH-1, not by NO3-1. And your equation for OH ions losing electrons to the battery is that it's you have to remember this equation. So it's 4 OH ions and they're going to lose electrons, and they would form two water molecules and an oxygen gas molecule, and four electrons are going to be produced. That's going to be your equation, and what you're going to notice over here is bubbles of O2 gas, or you can say effervescence. So you'll start noticing bubbles getting produced at your anode. So cathode, this is happening. Anode, this is happening. The OH ions are losing electrons. At cathode, it's the silver ions that are gaining electrons. So the OH ions are going to get used up. So what's going to happen to your solution? On one side, silver ions are gone. On the other side, you got OH ions that are gone. So what's left is H plus 1 and NO3 minus 1. So that means nitric acid is produced. So your silver nitrate eventually changes into nitric acid because the Ag plus 1 and the OH minus 1, they get used up. So that's the summary of electrolysis of silver nitrate aqueous using inert electrodes, which are graphite or platinum. So let's start another electrolysis now, and this time we're going to do an electrolysis of KBr aqueous. Now, when you have potassium bromide, KBr aqueous, you're going to have K's in group 1. So the ions that would be present in the solution are going to be K plus 1. You will also have Br, which is group 7, so it's minus 1. And since it's aqueous, so there's going to be H plus 1 and OH minus 1 ions as well. The negative cathode will attract all the positive ions in the solution, so they're going to go and stick to the cathode, negative cathode, so K plus 1. And your H plus 1, that would be coming from water, they're going to get attached to cathode. While your anode, the positive anode, that is connected to the positive battery terminal. And remember, these are inert graphite electrodes at the moment, or platinum electrodes. So Br minus 1 and OH minus 1, the negative ions will go in and get attached to anode. Now, the next thing that's going to happen is that somebody at cathode would gain electrons. The electrons are coming in. So it's either the electrons are either going to go to K plus 1 or they will be gained by H plus 1. So who's going to end up gaining electrons? We're going to look at our reactivity C's. So we've got K, which is right at the top. Okay, so K is over here. And we've got H, which is somewhere over here towards the bottom side. So remember, the ones that are at the bottom, these are the ions that are the ones that really like to gain electrons. So electrons coming in would be gained by, they're going to end up with H plus 1. H plus 1 will have a stronger attraction for electrons, and we can write an equation for that. So the equation is that H plus 1 needs an electron, and it will become neutral H. But your H is diatomic, so you would need to double it. And there's going to be two H atoms produced, and they will form H2 gas molecules. And what you'll notice is bubbles of a colorless gas. So what you'll notice over here is you'll see small bubbles forming around the cathode. So that's it. So we've figured out cathode. And at anode, someone over here is going to lose electrons. So whether it's Br minus 1 or OH minus 1, we're going to look at our series. So here's our series at anode, and the competition is between Br minus 1 or OH minus 1. So you can see that the Br is right at the bottom over here, while OH is slightly above that. So who loses electrons? The one that's at the lower side. So Br minus 1 is the one that's going to give the electrons to the battery. And your equation at anode would be that Br minus 1 would lose electrons, one electron, and it will form a neutral Br atom, but it's diatomic, so you're going to double it. And two Br atoms are going to be produced, and they would end up forming Br2 gas molecule. Now, Br2 is a volatile liquid, red-brown liquid. So that's going to form, plus it's a volatile. That means it's got a very low boiling point. So you're going to notice vapors of bromine that are going to be formed. Let's now move to the next subtopic, which is that we're going to try and do electrolysis using active electrodes. So what really are active electrodes? They are made from reactive metals. So unlike in the previous case, you had inert electrodes, now you've got reactive metals. And remember, what do metals like to do? Metals, they like to lose electrons, the reactive ones. So we're no longer using inert electrodes. Inert were graphite and platinum. We're not using them. Now we're using active electrodes, metals that really like to lose electrons. So same exact diagram. You've got your cathode, you've got your anode. Now, the first example, I'm going to do the electrolysis. Remember, we've got active electrodes now. I haven't discussed them. So the more common one that comes in your exams a lot, that's copper sulfate, aqueous. And the thing is, we'll be using electrodes that would be made out of copper metal. So the only difference now is, so this is electrolysis of copper sulfate aqueous using Cu electrodes, copper electrodes. And so that's the only difference. Copper is a metal; it's got a sea of free moving electrons, so it will be conducting electricity. But remember, copper metal is slightly more reactive, so it's not very inert. It's very slightly reactive, so it likes to lose electrons. So we're going to do the electrolysis just as before. There's nothing different, except there's going to be some changes that would happen at the anode. So these are the ions that are present in copper sulfate aqueous. I've got copper +2, I've got SO4 -2, and I've got it's aqueous, so I've got two ions from water as well. That's H+1 and OH -1. The positive ions in the solution, they're going to get attracted to the negative cathode. So copper ions H+1 getting attracted to cathode. On the other hand, OH -1 and SO4 -2, the negative ions will be attracted to your anode. So let's deal with the cathode first. The battery is going to send in electrons. And remember, it doesn't really matter what the cathode, which metal the cathode is made up of. Metals don't like to gain electrons. So the metallic copper over here is not going to do anything. It's just going to conduct electricity. It's not going to gain electrons. Metals don't form negative ions. So the copper metal over here is kind of irrelevant. It's not doing anything. So the electrons are coming in, and the electrons are going to be gained by either the copper ions in the solution or the H+1. So again, just a quick look at the ease of discharge series, the reactivity series, and you will notice that copper is over here, and you've got H over at the top. So the one that's at the unreactive metal and the ions, they're the ones that like to gain electrons. So it's going to be copper over here that's going to gain electrons. So I'm going to write the equation, which is that my Cu ions would gain electrons, and they would become copper. And you'll notice a pink metallic depositing on the cathode. So the cathode mass would start to increase, and a pink metallic deposit would start forming on top of the cathode. So again, I repeat, it doesn't really matter what the cathode is made up of. You're doing exactly the same what you were doing previously. Copper ions or H+1, who gains electrons? It's copper. Now the situation is going to be very different at the anode. This is where the difference is. Now when the electrode or anode is made out of a reactive metal, so we've already discussed that the metal, it likes to, when it's slightly reactive, it likes to lose electrons. So the battery is trying to pull electrons. Now the battery has three options. It can either take away electrons from the OH -1, or it can take away electrons from the SO4 -1, -2, or what it could do is that it could remove electrons from the copper metal itself. And that is exactly what it does. That the copper metal is the one that gets oxidized. It is the one that loses electrons. So the battery takes away electrons from the copper metal itself, from the anode itself. So the anode metal, it loses electrons and it dissolves. So slowly what will happen is, so nothing would happen to OH -1 or SO4 -2. These ions remain part of the solution. They don't end up losing electrons. So unlike in the previous case where you had to decide between OH and SO4, you don't have to decide that anymore. It's always going to be the copper metal that loses electrons. And when it does that, the copper metal anode would start to dissolve. Because the copper would lose electrons, so it will slowly disappear. And the copper metal would dissolve. It will start forming copper ions. So the anode would slowly lose mass. Every time battery takes away electrons, they're being taken away from copper, and the copper would start turning into copper ions. So the copper ions would go into the solution, and the concentration of copper ions would increase. Nothing would happen to OH -1 or SO4 -2, but slowly your anode would start disappearing. It will it will start to disappear because all the copper would start to dissolve and its mass would decrease. So here's your equation at your anode. And that's it. That's all you have to remember. You have to remember that whenever you've got an active electrode, it's always the copper metal that's the one, I mean, not the metal, whatever the metal is, that's the one that's going to end up losing electrons. But for that, you need a slightly reactive metal. So copper would dissolve and it will form copper ions. So I've got my two equations. On one side, you've got all the copper ions, the positive ions getting attracted to the negative cathode and they're gaining electrons, and copper metal is depositing. So their copper metal is getting formed. And at your anode, the copper is the one that's the metallic copper that the anode is made up of. It's losing electrons and it's turning into ions. And so it's dissolving. So the quantity of copper ions, so more copper ions are getting produced. So overall, nothing is happening. What is happening is on one side, copper is getting deposited. On the other side, more copper ions are getting formed. So on one side, the copper ions are getting used up. So they're being removed and they're turning into copper metal. On the other side, more copper ions are getting formed. So overall, no changes would happen in the solution. No change in solution. The blue colored copper sulfate would remain blue. Copper ions getting used up, they're turning into copper. More copper ions getting formed. So nothing happens to H plus 1, nothing happens to OH minus 1, nothing happens to the rest of the ions. And the quantity of copper ions also remains kind of constant. One side they're getting used up, one side they're getting produced. So we can write, so if they tell you to draw a mass diagram, remember the anode is losing mass and the cathode would be gaining mass. Do another electrolysis using active electrodes. Again, I'm using silver electrodes, silver cathode, silver anode, and I'm trying to do the electrolysis of silver nitrate aqueous. So quickly, I'm going to write down the ions. Now, the ions that are in the solution, silver nitrate, Ag is +1. Remember that. NO3 is -1. Aqueous means two ions from water, H +1 and OH ions. The negative cathode is going to attract all the positive ions. So all the thousands of silver ions and H +1 ions are going to get positive ions are going to get attracted to the negative cathode. And all my negative ions over here, OH -1 and NO3 -1, they will be attracted to my positive. They will be attracted to my positive anode. So, so over here at cathode, who's going to gain electrons? And again, the silver metal at the cathode is kind of pointless. It's not doing anything. Metals don't like to gain electrons. So the electrons are coming in. So someone in the solution has to gain electrons. It's either going to be silver +1 or Ag +1. So if you look at the reactivity C, silver is over here and H is over here. So you got H and you got Ag. So the ones that at the bottom, that's the one that's more likely to gain electrons. So the electrons are going to go to silver, and we'll write our equation. Silver ions, they would gain 1 electron and they would turn into neutral silver metallic atoms. So you'll start noticing metallic silver depositing on the cathode. Its mass would increase. So metallic shiny silver deposit. Silver is obviously silverish. So you'll see a shiny metal deposit over here. And now move to anode. What's going to happen at anode? Again, remember that active electrode metals like to lose electrons. So battery is trying to pull electrons. Now, again, the same thing. Whenever you have an active electrode, it's the anode that's going to be different. So when the battery pulls electrons, it's not going to take away electrons from the OH -1 or NO3 -1. You don't have to worry about the ions in the solution. The battery is going to remove electrons from the silver metal itself. So your silver metal over here would lose electrons and it will turn into silver ions. So it will lose electrons and it will turn into silver ions. Battery is going to remove electrons from the silver itself. So your anode would start to dissolve because a lot of silver ions are going to be produced. So your anode would start to lose mass. It would start to atoms in the anode, silver atoms would start losing electrons and they will start forming silver ions which are going to dissolve in the solution. So lots of atoms turning into silver ions going into the solution. And obviously these are positive ions, so they're going to get attracted to the cathode anyways. And when they go there, they're going to gain electrons, so they're going to form silver back again. So what is happening is that the anode dissolves slowly. It gets oxidized, it loses electrons. OH minus 1, NO3 minus 1, nothing happens to them. So this on the anode side, the quantity of silver ions, it continues to increase. While at the cathode side, the same silver ions which get attracted to the cathode, the negative cathode, would gain electrons and they will turn back into silver. So the silver will deposit on the cathode. So what's basically happening is silver is dissolving at one side and the same silver ions are getting deposited as a metal, as a neutral metal atom on the other side when they gain electrons back. So silver from here would shift to the cathode. That's what's happening. So there would be no changes in solution because H plus 1, nothing happens to it. NO3, OH, nothing happens to it. What happens to silver ions? They get used up on one side, they get produced at the other side. So the net quantity of silver ions in the solution would also remain kind of unchanged. So no changes happening. Are happening in the solution. Now listen to this carefully. You've understood the process of active electrodes. Silver dissolving on one side and silver getting deposited on the other side. Now this is a very useful method when it comes to electroplating. When you want to cover, let's say you've got a spoon that's made out of a very cheap metal and you want to cover that spoon with silver. So what you're going to do is you can place the spoon over here. Silver will dissolve over here. The battery would take away electrons. It will form silver ions and the positive silver ions will get attracted to the negative cathode, where they will gain electrons from the battery and they'll deposit on whatever object you place. You can place any metallic object. You can place a watch over here. You can place a spoon over here. It's going to get coated with silver. So we're just going to continue what we're doing. We're now going to learn how to electroplate. And the example is we're going to try and electroplate a metallic spoon. Remember, the object has to conduct electricity. If it's not able to conduct electricity, then you're not going to have an electrolysis. The electrons won't be able to move around. So you need a metallic object. So how do you electroplate a spoon with metallic silver? Now here I've drawn a diagram for electroplating, and remember I'm going to try and electroplate the spoon with silver. Now there's certain rules that need to be followed. So remember these 3 rules. So 3 rules. One is that the object has to be at cathode, the negative electrode. So if I'm electroplating a spoon, the spoon must be connected to the cathode, and the spoon must be a conducting material because you want electrons to flow. So if you can't electroplate a piece of wood because it's the electrons will not be able to flow through the piece of wood. So the spoon has to be at the cathode. The anode must be made of the electroplating metal. So if I want to electroplate a spoon with silver, this anode over here has to be made out of silver. So it's got to be made out of Ag, which is silver. And then the last thing is that the solution must contain electroplating metal ions. So if I want to electroplate it with silver, the solution over here, the electrolyte, must contain either it's aqueous or molten. It must contain silver ions. So you need a compound. So for silver, I can go with silver nitrate, aqueous. Nitrates are easy to choose because the thing with nitrates is that they're all soluble. You want a compound that is going to dissolve in water and form a solution. So silver nitrate is the best. Nitrates are all soluble, remember that. So if you want to electroplate something with copper, like if I wanted to electroplate this spoon with copper, I'm going to put copper metal at the anode and I'm going to choose a solution that contains copper ions. So copper nitrate would do the job because all nitrates are soluble. Even copper sulfate would work. But remember, whatever compound you choose, it has to be a soluble compound. So again, let's just like the last time, what's going to happen? The solution is going to have, you've got silver nitrate. So the solution at the negative side, silver ions are going to get attracted to the spoon because it's the cathode. The NO3 minus 1 ions are going to get attracted to the anode because positive will attract the negative ions. And it's aqueous, so that means you've got 2 more ions. One is H plus 1, so lots of H plus 1 ions, and lots of OH ions. OH ions will get attracted to the anode. And the H plus 1 ions in the solution, the millions of H plus 1 ions will get attracted to the cathode. Now, electrons would come in, so you've got 2 choices. Who's going to gain the electrons? Is it silver plus 1 or is it H plus 1? So we can have a look at the previous example. Silver is over here and H is over here. So it's obviously going to be silver that would, the one that's lower in the reactivity, that's the one that's going to end up gaining electrons. So let's go back to our example. The electrons would be gained by silver. So all the electrons that are coming from the battery, they will end up with silver, and your equation is this one. The silver ions would gain 1 electron and they will form silver. So what you'll notice is you'll start noticing a coating of silver metal deposit on the spoon. So my spoon will start getting a coating of shiny silver. So it will start looking really nice. And what will happen at the anode? The battery is going to take away electrons. And remember what we just discussed, that if it's an active electrode, if it's made from a metal that's slightly reactive, not inert, not completely inert, the electrons are going to be lost by the metal itself. Metals like to lose electrons. NO3 minus 1 and OH minus 1 are not the ones that are going to lose electrons. It's the silver metal that would lose electrons. And my equation would be that the silver metal would lose electrons and it will form positive ions, and the electron will be lost. And always remember, silver is always plus 1. So the anode will start producing Ag plus 1 ions. It will slowly start to dissolve. It will start getting used up and it will start to dissolve. So this is how electroplating is happening. One side is producing silver ions, the anode is dissolving and it's producing more silver ions. And the same silver ions they're getting attracted to the negative cathode, where they're gaining electrons back from the battery and they're turning into silver. So the silver over here will slowly start coating the spoon that you have over here, and silver will start depositing. So just remember the three rules for electroplating. The three rules are that the object should always be placed at cathode. So if I want to electroplate a watch with silver, I'm going to place the watch. I'm going to place it at cathode. The anode must be made from the metal that you want to electroplate. So if I want to electroplate it using gold, I'm going to put gold over here. And the solution must contain electroplating metal ions. So the solution, if I want to electroplate it with gold, it must be a gold compound, maybe gold nitrate or something, gold chloride, or even some molten gold compound. And some things about if you want to do a more effective or a thicker, or you want to do the electroplating quickly, what you need is, so for a faster electroplating or to get a more thicker plate, you obviously need more current. You want more electrons to flow through the circuit so that more silver ions get deposited. You need more concentration. So if you have more ions in the solution overall, there's going to be much faster reaction. And you need a longer time as well. So if you want to get a thicker plate, you need to do electroplating for a much longer time so that more silver gets deposited. Now let's try to electroplate a key with copper. So again, the three rules. The key has to be made the cathode. So I've drawn the diagram. I've attached the key over here to my negative terminal of the battery, which is the cathode. Uh, Now, if I want to electroplate it with copper, what I need to do is I need to make the anode should be made out of copper. So there's going to be a copper plate. I'm going to put it, I'm going to connect it with the positive terminal of the battery. So the anode is copper. And the solution, because I'm electroplating it with copper, it should contain copper ions. So copper ions can be added to the solution in the form of copper sulfate. It has to be a copper compound. So copper sulfate, remember nitrates are all soluble. So copper nitrate is also good. Copper chloride is also good because that's also going to contain copper ions. So any soluble compound of copper which contains copper plus 2 ions and it's soluble, it has to be very soluble. So I'm going to start the process. I'm going to turn on the switch and electroplating would start. So the copper sulfate has 4 ions. So it's got copper ions and sulfate ions, and it's got H plus 1 NOH ion because it's aqueous. They're coming from the solution. The positive ions are going to go and stick to the negative cathode, while the negative ions, the OH minus 1 and SO4 minus 2, will go and get attached to the positive anode. The battery is going to send in electrons. So the electrons would either go to copper plus 2 or they're going to go to H plus 1. So one of them has a stronger tendency between the two to gain electrons. And we're going to find this out by looking at the reactivity series. So there's one open over here. So copper is over here, if you can see clearly, and H is over here. So copper is the one that's lower in the reactivity series. So copper is the one that's going to gain electrons. So it's definitely going to be, where's our diagram? So it's definitely, the electrons would definitely be going to copper. And I'm going to write down the equation. And so you can see the copper ions plus 2 gaining 2 electrons forming copper, and you'll see a pink metal depositing on top of the key. So the key would start getting electroplated by copper. It's going to get covered by copper. Not the whole of it, the part that is dipped. So if you want to cover the whole key with copper, you would have to like dip the entire key into the solution. So the an even coating of the metal will deposit, and the key has to be kept very clean so that the copper metal attaches to the surface of the copper and completely coats it. Now, on the anode side, the battery is going to take away electrons. And remember, I told you that if the electrode is made out of a metal, a slightly reactive metal, then the electrons would be lost by the metal itself. So the equation at your anode would be that your copper metal would lose electrons and it will turn into positive ions. And those electrons would be lost to the battery. So copper would start to dissolve. It will start forming copper ions. And so in your solution, more copper ions are going to be formed. Your anode will start to dissolve. So there'll be chunks coming out of it. The metal atoms, the copper atoms would turn into copper ions, which will go into the solution. So the anode starts to lose mass and the anode dissolves. And that's it. That's your key getting electroplated. On one side, the copper is dissolving, forming copper ions. Battery is taking away electrons from it. So more copper ions are being produced. And those same copper ions are getting attracted to the negative cathode, where they are lower in the reactivity series. So they're the ones that gain electrons and they form copper. So the pink metal gets deposited on top of the key. So slowly the copper ions dissolve and they get deposited on the key on the other side. So remember these three rules for electroplating. Now, the one last thing that we're going to do about electrolysis is we're going to talk about purification of copper from copper ores. And let me explain this. This is something that's related to extraction of metals, but the exact same concept that we're doing, we're going to apply the same electroplating concept to the purification of copper as well. So let me show you copper ores first. So here in front of us, there's an example of a copper ore. So there's a rock with a lot of impurities, but there's pure copper, the golden brown copper. That's basically pure copper metal that's present over here. Now it's very impure. If I melt it or do anything with it, there's a lot of other particles that are part of this ore which are impurities. So what I'm going to do is I'm going to purify this copper, and the way I'm going to do this is just like electroplating. So here I've drawn a diagram. So just remember that the ore that you've obtained, the impure ore that contains the copper, you're going to place it at the anode, at the positive side. That's rule number one. You have written all the rules on the left side. The pure copper has to be, a thin, tiny piece of pure copper has to be at the cathode. That's your negative side. And your solution over here, the solution at the bottom, that must be containing copper ions. So we can have what we can have is we can have a copper sulfate aqueous solution. So any compound of copper 2 plus ions that would do the job. Copper nitrate or copper chloride, any copper compound which contains copper plus 2 ions. So my solution over here right now has copper plus 2 ions. It's got SO4 minus 2 and it's aqueous, so it's got H plus 1 and it's got OH minus 1. Now what's going to happen is the same exact thing that we are doing right now. So what's going to happen is the battery at the anode would take away electrons. So electrons would be pulled from the anode, and remember it's made out of copper metal. So the electrons would not be lost from the OH minus 1 or SO4 minus 2 ions. They're going to be lost by the copper that's trapped in this ore over here. So what is going to happen at the anode is that the copper would start losing electrons. It will start turning into copper ions. And the copper would start dissolving. It will start turning into copper ions. Those ions would leave the ore. Those ions will dissolve. And they'll go into the solution. So the battery pulls away electrons. The copper metal, which is over here trapped in this rock, they would start to lose electrons. They will start turning into copper ions. So your copper will start to dissolve. The impurities, all the rest of the impurities, the rocks and the sand, etc., they would all stay behind. And you'll have copper ions forming in the solution. And then at the cathode, the positive ions are going to get attracted to the negative cathode. So over there, the battery is going to send in electrons. And copper ions are lower in the reactivities, so compared to H. I mean, we've seen the reactivities a lot. So copper ions, you should remember, are lower in the reactivities, so they've got a greater tendency to actually gain electrons. So over here, the equation will be that the copper ions would end up gaining those electrons back from the battery, and they'll turn back into copper. So you'll start seeing a deposit of copper building up at your